Okay, welcome everyone to the second hour. For those of you who couldn't watch the first hour, you missed a lot. You missed the nice combinatorial introduction. I will continue with algebraic, or if you want, analytic part of the introduction. And let me ask you the question I just told you. How many of you were fascinated by the exponential function back in calculus? Very good, thank you so much. So, we know that the exponential function e to z, the exponential function, can be expanded as a series, yes? A series, a power series in z. So if we want to write this as if we don't know, a sub n, z to n, because this is a power series, z assumes non-negative integral powers n running from 0 to infinity. The next piece of information we know to extract these coefficients is that the exponential function is its own derivative. So if we take the derivative with respect to z on both sides, we end up with the same function here. And if we take the derivative on the right-hand side, assuming absolute convergence, for now, assuming absolute convergence, you have n times a sub n, z to n minus 1. And we know that once two power series are identical to each other, then the coefficients must agree. So if we adjust for the power of z here, we must have a sub n minus 1 equals n times a sub n. In other words, a sub n must be a sub n minus 1 divided by n. And if we iterate this against itself, we will find that a sub n equals a sub 0 divided by n factorial, where, you know, factorial is the product of numbers from 1 to whichever natural number we gave there. And the question comes down to finding a0. A0 is nothing but the constant number here. Plug in z equals 0. A sub 0 equals e to 0, which is 1, and we are done. Therefore, the exponential function is from n equals 0 to infinity, z to n divided by n factorial. At this point, we can address the convergence questions whenever we have factorials floating around. The ratio test is your friend. And you will deduce that this converges absolutely for all z, and then we have the power series expansion. I don't suppose we have any questions at this point. Okay. Now we will play the same game in a Q setting. And then I will sweep a lot under the rug. Because of time constraints, I will not make all connections we can do. But if you are interested in this stuff, I can suggest you read some books. Instead of the exponential function, now I'll give you Q Hammer symbols as Joanne gave us in the previous hour. And for technical reasons, I'll give you the infinite products up front. So ask me why after the lecture, okay? So we will try the same stunt. For the ratio of two infinite products, a times z q sub infinity divided by z semicolon q sub infinity. We will regard this as an analytic function. We don't know if it's analytic yet, but take my word for it. We will take this as an analytic function in z, and we will try to find a power series for this guy. So call it big F of z. I'm not going to write q because q is going to be everywhere. Know that q is there, even if we don't write it. So once again, for now, assume that this is an analytic function. And we will try and find a power series representation for it. Now, what happens if we multiply z by q? Or what happens if we replace z by zq? At this point, let's remember the definitions for these infinite products. So upstairs is 1 minus a times z. We begin with the parameter there. And in every next factor we write, we multiply this by q. 1 minus a times z times q, 1 minus a times z times q squared, and so on. And downstairs is, the denominator is 1 minus z times q, 1 minus z times q squared, and so on. If we were to write f of z times q, then we have to replace z by zq here, and this z by z times q as well. Which means that the first factor, both in the numerator and the denominator, will be left out, and the rest of the factors will be combined to give you f times z cubed. So what's in front? 1 minus a z divided by 1 minus z. And this is nothing but fz. Now, any questions at this point? This is the first checkpoint. Are we in tandem? Is everybody following up to here? Okay. Then, if we write f as a power series, the right-hand side is, what is it from n equals 0 to infinity, a sub n, z to n. The left-hand side is going to be this rational function in front divided by 1 minus z times the same sum where z is replaced by z times q. So from n equals 0 to infinity, a sub n, z times q, the quantity z times q to n, which is z to n, q to n. And then we clear the denominator by cross-multiplying. And then we distribute those terms through the sums. Let's see what we get. So on the left-hand side, 1 minus z is gone. And we have from n equals 0 to infinity, a sub n, q to n, z to n, minus a times z times that guy, n equals 0 to infinity, a times a sub n, sorry about the profusion of a's here, q to n, z to n plus 1, right? Yes, because we have an extra z there. And on the right-hand side, n equals 0 to infinity, a sub n, z to n, minus n equals 0 to infinity, a sub n, z to n plus 1. We are almost there. We need to shift the index in the second sums both on the right-hand side and on the left, which will give us n must be replaced by n minus 1, so we have the same power of z throughout. From n equals 1 to infinity, a times a sub n minus 1, q to n minus 1, times z to n here for the second sum on the left, Something similar for the second sum on the right. N equals 1 to infinity, a sub n minus 1, z to n. Now we can identify coefficients of z to n, both on the left and on the right. What is it? A sub n times q to n minus a times a sub n minus 1 q to n minus 1 will be identical to the coefficient of z to n on the right. Sorry, a sub n minus a sub n minus 1. Did I forget anything? I think we're good. Yes, okay. Then we change gears. Instead of shooting for powers of z here, we will shoot for relating a sub n to a sub n minus 1. So we have a recurrence between the two. We collect all a sub n's on one side, all a sub n minus 1's on the opposite side. So a sub n 1 minus q to n here is gonna be a sub n minus 1, and inside the parentheses we have, what do we have? 1 minus a times q to n minus 1. In other words, a sub n is gonna be a sub n minus 1 times its rational function. Now we can rewrite this n replaced by n minus 1 on the next line, n replaced by n minus 2 on the next line, and so on. We can multiply side by side, which amounts to using this recurrence against itself to find the infinite product. Ratio of infinite products we started with is from n equals 0 to infinity, a sub 0 times 1 minus a upstairs, 1 minus a times q, 1 minus a times q squared, 1 minus a times q to n minus 1 up to there, n factors upstairs, n factors downstairs, which are 1 minus q, 1 minus q squared, 1 minus q to n. What did we forget? Well, remember this was the coefficient of z to n. And we are done. Well, we are almost done, except that we haven't determined this a sub 0. But behold, this is the power series expansion for this infinite product. And to find a0, remember a0 is the constant number, the constant term, plug in z equals 0 here. But once you put z equals 0, what did this thing represent? 1 minus a times z, 1 minus 0 times 1 minus another 0, 1 minus another 0. So product of all ones upstairs, product of all ones in the denominator. Therefore, a0 will be 1. So, ladies and gentlemen, behold the Q binomial theorem. The very first Q series identity, no, the very second Q series identity we saw today. Any questions? I'm deliberately not making connections to partitions because other speakers will make lots of connections to partitions. I just want to show you the algebraic side, the the algebraic or the analytic side, which operations we can do, which operations we cannot do, and so on. Of course, we can write this in the compact notation using Q-Pockhammer symbols. So for the record, let's write the theorem here, and let's keep it on the board because we'll be building on it. So the Q binomial theorem using the Q-Pockhammer symbol notation we saw in the previous hour. AG Q sub infinity divided by G Q sub infinity equals the series from n equals 0 to infinity A Q sub n divided by Q Q sub n Z to n. You must ask a question here. Please ask me that question. Too bad I didn't give you the question before. But please find a question to ask me here. Yes?
Are we sure it converges?
Oh, okay, that's question number 0. How do we know that this converges? Very good. Does this even converge? So for the left-hand side, take logarithms. So that you convert products into sums and then use the ratio test. For the right-hand side, use the ratio test without taking logarithms. In both instances, you will see that if you take Q less than 1 in modulus, less than 1 in absolute value, both the product and the series converge absolutely. Çok yaşa. So we have absolute convergence. In fact, for the duration of this week, all series, all products you're going to see will absolutely converge when Q is less than 1. If you feel the need to put more restrictions, you can find explicit convergence conditions. So convergence for us is of secondary importance. All right. So that's question number 0. More important than the first one, but what's the first question here? Yes?
Why binomial?
Exactly. Thank you so much. Why do we call it the Q binomial theorem? To answer this question, we'll make a substitution in this theorem, and we will let A be a positive power of Q. Let A be Q to M for some positive M. For some positive integer M. And then let's see what happens, because there will be lots of cancellations for the infinite products. Upstairs is going to be Z times Q to M, 1 minus Z times Q to M, 1 minus Z times Q to M plus 1, 1 minus z times q to m plus 2, and so on. Where downstairs is 1 minus z, so the numerator has a head start. 1 minus z times q, 1 minus z times q squared, but at some point the denominator will catch up with the numerator. 1 minus z q to m minus 1, almost there. And after this point, everything is common between the numerator and the denominator. So these are going to go. The infinite products will turn into a finite product in the denominator. And then we'll have something similar. Well, we will not have something similar on the right-hand side. We'll just make the substitution there. So we have 1 over 1 minus zq up to 1 minus zq to m minus 1 equals the sum, n running from 0 to infinity, 1 minus q to m, 1 minus q to m plus 1, and so on, 1 minus q to what? M plus n minus 1. Over 1 minus q squared, 1 minus q to n, z to n. Take the limit as q goes to 1. And if you are cautious, let q tend to 1 from the left. Use L'Hopital's rule as many times as necessary inside the sum, because this is absolutely convergent. We can interchange the limit and the summation, and we can take the limit of this guy, that guy. All of these factors pair nicely. Please don't make me spell L'Hopital's rule here. On the right-hand side, we have 1 over 1 minus z raised to m. And on the right-hand side, we have minus m divided by minus 1, m divided by 1, m plus 1 divided by 2, m plus 2 divided by 3, and so on. Basically, we have n factorial downstairs. And upstairs, we have m plus 1, m plus 2. If you stare at this for long enough, you'll be convinced that it's nothing but a binomial coefficient. This is going to be m plus n minus 1. Choose n, z to n. So you have the binomial series. This is why we call it the Q binomial theorem up front. These are the two questions I had in mind. After this, fire at will. Any other questions? If you happen to have any questions, just interrupt. Now let's play some games. I'll show you two things. One easy, the other is a little bit more involved, but not too difficult altogether. So what happens if we put a equals 0 here? In the Q binomial theorem, if we put a equals 0, and on the right-hand side, the top factor will be gone. Yes? Plug in the parameter equals 0, and then you will be multiplying 1 minus 0, 1 minus 0, 1 minus 0, all the way to the infinity. So upstairs will be 1. And inside the summation, again, the numerator is going to be 0, semicolon q sub n, which is just 1. If we plug in A equals 0, this is one of the basic methods to reduce known identities to newer ones, or to produce more identities. Then we will have 1 over z semicolon q sub infinity equals, from n equals 0 to infinity, z to n divided by q sub n. Many of us call this the q factorial. For obvious reasons. Look at the previous slide. If we multiply it with necessary factors, or if we use z for a substitution, if we take the limit as q goes to 1, this really will be n factorial downstairs here. For these reasons, this function, along with its expansion, this is called the q exponential function. Let me say a q exponential function. That's one thing. This was the easier one. And please make the connection with the exponential function, the exponential function we got the series of at the beginning. The next thing is, before taking a limit, we'll do a change of parameters here. We'll shift a to the denominator. How can we do that? Well, if we replace z by z divided by a, now replace z by z over a. Let's see what we're going to have. We will have z semicolon q sub infinity divided by z divided by a semicolon q sub infinity. That is from n equals 0 to infinity, except for z, everything else is the same. We have a q sub n, q sub n, z to n divided by a to n. Now, take the limit as a tends to infinity. Excuse me, a tends to infinity. Because we have absolute convergence, we can interpret limits in the obvious way. We can take the limit factor by factor on the left, and we can take the limit term by term on the right. This is going to go to 0. Yes, because the denominator in the parameter grows without bounds, therefore it goes to 0, which means that the denominator factor approaches 1. On the left, we are left with zq sub infinity. But what to do on the right? On the one hand, we have a in the denominator because this is growing without bounds. It's tempting to say that terms are approaching 0, but no. We have a's upstairs as well. So we have to examine the interplay. We have to quantify the interplay between the numerator and the denominator here. We can do it in two different ways. Either you find a different formula relating one Q Pockhammer symbol to another, or you just replace things by the definition and do the algebraic manipulations. We'll go the second way. So let's take z to n and q sub n aside, and let's focus on the remaining factors. A q sub n, a semicolon q sub n, divided by a to n. And just remember that we have z to n times the q factorial here. Write the definition for the numerator, 1 minus a times q, 1 minus a times q squared, 1 minus a times q to n minus 1. How many factors? Exactly n factors. Give 1a to each of these factors and write divided by a, divided by a, divided by a, divided by a. And then perform the fractional subtraction. No, separate the fractions, which means that you have 1 minus, no, 1 over a minus 1, 1 over a minus q, 1 over a minus q squared, 1 over a minus q to n minus 1. Now, all of these guys are going to be zeros. Now we are good. But we have some other accumulating factors here. For instance, we have a bunch of minus signs, which we can write. How many of them are there? Minus 1 to n. What else? We have q to 0 plus 1 plus 2. Lovely law of exponents up to n minus 1. And believe it or not, sum of first n minus 1 integers, n minus 1 times n divided by 2, right? Some people leave it this way. I prefer to write it as n choose 2 here, the binomial coefficient. So, if we plug things in place, we will have z semicolon q sub infinity, no denominator. This is going to be n running from 0 to infinity, minus 1 to n, q to n choose 2, z to n divided by q sub n. This is the second formula we can derive using the Q binomial theorem, or the second corollary of the Q binomial theorem. Any questions here? By the way, we did things systematically and we proved the Q binomial theorem first, got two corollaries afterwards. Both of these corollaries are named theorems. Both of these corollaries are named theorems, though the names escape me at the moment. Okay, we will change gears once again, so please look at the board and tell me if you have any questions. These are really rudimentary operations and we have to be fluent with them, because if we want to do integer partitions, we must be able to manipulate the generating functions, and this is the machinery. These are really the fundamental, the basic operations. And I'm sure you took discrete mathematics class, yes? You remember all those techniques from discrete mathematics. This is much more structured than discrete mathematics. There's a hierarchy of formulas. There's the Q binomial theorem, its corollaries. Next, we will see Heine's transformation, its corollaries. And then we will quantify the number of parameters appearing, and we will talk about hierarchy of formulas. Everything is very mechanical. Okay, let's keep the Q binomial theorem there, and I will erase the corollaries. Once again, if you happen to have any questions, feel free to interrupt. What time did I start? 24. Okay, so, okay, very good. We can state and prove Highness transformation, and we can even see some corollaries of Highness transformation. So the next significant theorem after the Q binomial theorem is Highness transformation. And once again, we are sweeping a lot under the rug because we have to mention the history of these things, the development of these things, and the connections to binomial coefficients as we know them, hypergeometric series as we know them, geometric to hypergeometric, and so on. But because of time limitations, I'm just showing you this corner of the theory. Just know that there are lots of connections. Anyway, I'm not going to state the theorem. We will prove the theorem, and we will take the ends and write it as Highness transformation formula. This time, we will have 2 plus 2 Pockhammer symbols in the numerator and in the denominator. Q Pockhammer symbols. In a Q hypergeometric sum. What do I mean by that? Instead of having A semicolon Q sub n, we will have another parameter. And guess what? It's going to be called B. Q sub n divided by one of the 2 denominator factors will be Q sub n. It's traditional now. We can do without. We cannot do without it. So it's always there. That's the first factor. The second factor is C. Semicolon Q sub n, Z to n. Now here's the forced question. Can we find a way to apply the Q binomial theorem in this setting? Can we force apply the Q binomial theorem here? And the answer is yes. Because we will force the application. How are we going to force the application? We choose these 2 victims and we imagine that they were infinite products. Instead of B Q sub n, C Q sub n, if these were infinite products, then we could apply the Q binomial theorem. But unfortunately, they are not infinite products. Can we make them? Yes, we can. So let's do it. This is one of the main methods in the theory. You see it for the first time. Maybe you are fascinated for a fraction of a second, and then that's just an ordinary method to you, and you will use it in other contexts. So if it was BQ sub infinity divided by CQ sub infinity, it isn't. Why not? Because we are missing some factors. Well, multiply and divide by the missing factors. So, until when does this go? 1 minus b times q, 1 minus b times q squared, 1 minus b times q to n minus 1. What's missing? 1 minus b times q to n. 1 minus b times q to n plus 1, and so on. Make the simplification between the 2, and you'll be left with this finite product. Do the same for C. Supply and take away the missing factors, CQ to n, 1 minus CQ to n plus 1, and so on. Perform the simplification, CQ sub n. And if you stare at this for long enough, you'll be convinced that this numerator is nothing but C times Q to n, Q sub infinity, and this is B times Q to n, Q sub infinity. Now we found the infinite products we were looking for. Let's plug them in place. And notice that, let me get another color here. This is independent of the index of summation, so we can take it out. So if we rewrite the very same series, this is going to be, after some missing steps, ask me if you cannot follow anything, BQ sub infinity divided by CQ sub infinity times the series, and running from 0 to infinity, AQ sub n, Z to n, divided by QQ sub n. And what are the remaining factors? The ones boxed in pink. CQ to n, Q infinity, BQ to n, Q infinity. We will apply the Q binomial theorem to these two guys. What do we want? We want this to be A times Z in the binomial theorem. And that is going to be Z in the Q binomial theorem. Not the Z here, but the Z in Q binomial theorem. So, well, we already have Z there. What's going to be A? A is the ratio of these two components, these two parameters, CQ to n divided by BQ to n. Q to n's will simplify, so A is going to be C divided by B. And we have to write it as another sum, a sum inside another one, and we will use a second index there. Let's use m. M running from 0 to infinity. What did we say A is? C divided by B, Q sub m divided by Q, Q sub m. What's Z? Z is B times Q to n. B to m, Q to m times n. Okay, let this be a checkpoint. Does anyone have questions? If you're not taking notes, you'll fall asleep in 2 minutes. We are doing college algebra, yes, but it's the application that counts, okay? The next operation is switching the order of summation here and finding another way to apply the Q binomial theorem, and then that's going to be it. And how can we switch the order of summations here? If we are worried about convergence, take my word for it, these are absolutely convergent if you take Q less than 1 in modulus. Anyway, switch the order of summations here. BQ sub infinity, CQ sub infinity, Now the outer sum will be over m. This can be factored out of the first summation. This can be factored out. B to m may be factored out. This has to stay in because this both depends on m and n. So it has to stay inside. So we have C divided by B, Q sub m, Q sub m, and running from 0 to infinity, A sub Q, A Q sub n, Q sub n. We want something raised to n. What's that something? Z times Q to m. Use the Q binomial theorem one more time. Did I? Ah, yes, you're right. Yes, thank you. So there is B to M here, yes. What else? I think we're good. Yeah, we're good. Use the Q binomial theorem there. Make the connections. A plays itself, and Z is replaced by Z times Q to M. Yes. Yes, we need the beginning. This is the intermediate part, and now we continue here. Write everything up to the last summation, the inside summation. B sub infinity, C sub infinity, m greater than or equal to 0, C over B sub m, B to m. Bear with me for a moment, we are almost there. The Q factorial downstairs, and then we said apply the Q binomial theorem. What's A times Z? A times Z times Q to M. Q sub infinity. And Z is Z times Q to M sub infinity. I wish I didn't erase that part, but this is nothing but AZ sub infinity. Just supply and take out the missing factors. ZQ sub infinity. What are the missing factors? They are exactly ZQ sub M, AZQ sub M. Once we do that, we are done. We can take these two guys out as well. So we have B, A times Z, C, and Z. And inside the summation, which parameters do we have? C divided by B and Z. And downstairs we have Q and A times C. And what did we forget? B to M. Okay, that's the end of the derivation. Look where we started. And look where we ended. This is Highness Q series transformation. Let's write it using yet another shorthand. Heine's theorem is 2 phi 1 A, B, and C, Q, and Z. Well, if you look at the sum over there, no, the sum over there, the notation is self-explanatory. 2 is number of upstairs factors. Numerator parameters. 1 is number of denominator parameters. Numerator parameters, denominator parameters. The Q factorial is always there. Q is the base we are using, and Z is the argument. So Heine's theorem stipulates that this equals, what did the sum spit out? We have B and A times Z, Q infinity, divided by C and Z infinity. Again, this notation is self-explanatory. If we have two infinite products with the same base, we can combine them like this. This is just notation. Is 2 phi 1. And the denominator, the numerator factors are C divided by B, and what is it? Z. We have A times Z here, the base is Q, and the argument is B. You can read a lot into Heine's theorem. For instance, it's very obvious that on the left-hand side you can switch A and B, right? And you will get the same series. Switch A and B here. Who's going to convince us that we are going to have the same series? It's very not obvious that this is symmetric in A and B. This one is obviously symmetric in A and B. This one is not. But anyway, that's Heine's theorem. Using the same notation, the Q binomial theorem may be written as follows. This becomes 1 phi 0, A, nothing in the denominator, Q and Z.
What is phi stand for?
Say it again.
This phi, you said that would be the phi 1. This notation is a phi number.
Yes?
So what is this one? So phi 1.
Are we talking about the Q binomial theorem?
No, this is in Heine's theorem.
Two upstairs.
The notation phi 1.
2 phi 1, yes.
Yeah, what is this phi 1?
It's 2 phi 1 together.
Yeah.
So that's the name. This whole thing is the name of the function. Whatever you write on the left, that's the number of parameters in the numerator. Whatever you write on the right is the number of parameters in the denominator. Okay? It's combined. One letter, two numbers. So Q binomial theorem is 1 phi 0, and this is the hierarchy of formulas I mentioned 10 minutes ago. Q binomial theorem is 1 phi 0, Heine's transformation is 2 phi 1, and then we have transformations for 3 phi 2, 4 phi 3, 5 phi 4, and so on. So they are built on top of each other. And this is the very top or the very bottom, depending on your point of view. Any other questions? Once again, we are doing nothing but high school algebra here, but it's the application that counts. Now let's see some corollaries of Heine's transformation. We needed this shorthand. It's not just for show, it's for convenience. So 2 phi 1, A, B, C, Q, and Z We said that it's the ratio of two infinite products. Another similar series where the parameters are C over B, Z, and downstairs we have A times C. Now we really need colors here. Forget about the infinite products in the front for a moment and take this as A, take this as B, take this as Z, and take this as C. I'm not going to do this because you will come back to where you've started. The B and Z will change places as well. However, if you switch these two parameters, if you write Z here, C divided by B there, apply Heinz transformation, you will find yet another thing. So let's write it down. We have the same infinite product here. It will come into play a moment later. Well, okay. Let's write it anyhow. B, A times Z. Okay. Don't see this. Now, what's B? Well, we have C divided by B. What's A times Z? That's B times Z now. And downstairs we have C. What's C? That's A times Z. And finally, we have Z, but Z is played by B now. Color coding is important, otherwise we lose track of what we're doing. And then the first parameter must be Z there. Okay, we gain B back. The second parameter must be C divided by B, C divided by B. So it's ABZ divided by C. Downstairs parameter is A times Z. That's B times Z now. What was B? It's C divided by B. And then there are simplifications here. For instance, BQ infinity goes away. A times ZQ sub infinity goes away. We are left with C divided by B, B times C, C and Z, Q sub infinities. And this is called the second iterative of Heinz transformation. And we can keep going. Of course, we have finitely many parameters. We have a fixed number of parameters there. Even if we could take all permutations of these letters, we have so many iterations we can work with, yes? So you can do this 6 times. But only the 3 of them are really important because the first 3 and the last 3 are Heinz transformation written in this form. And if we switch B and A up front, they are going to be the last 3. So the first, second, and third iterative of Heinz transformations, they are really what count. Unfortunately, we won't have time to talk about yet a reduction of Heinz third iterate, but I want to write it. Please bear with me for a moment. I want to write the third iterative of Heinz transformation. Keep it in your notes because in the next hour we will continue with that. So this time, let me choose yet another color. This is gonna play A, this is gonna play B, this is gonna be Z, and this is gonna be C. I think so, yes. So don't forget where it comes from. C divided by B and B times Z Q sub infinity over another two infinite products. Now, Z is C divided by B. C divided by B here is that divided by this. It's C divided by A. And the third parameter is B times Z. B times Z is, we are back to C. And what's going to be the argument? The argument is going to be C divided by B, C divided by B. Wait, no. No, the argument is going to be B, ABZ divided by C. And then what did we forget? We forgot the infinite products here, which are B and AZ, C divided by B, C divided by, wait. I think I'm messing up big time. B is ABZ divided by C. A times Z is C. Okay, now we are good. C is B times Z. And finally, Z is, what is it? C divided by B. Okay. Now there are a bunch of cancellations again. C divided by B are gone. What else? B times Z is gone. What else? C is gone. And this one stays, that one stays. That's it for this hour. Thank you for your patience. And believe me, we will connect this to partitions later. And once again, I promise to give you a proof of Rogers-Ramanujan identities using this machinery. So tedious way, but nice product in the end. Thank you for your attention.